Hi, this is Mr. Max. I am going to do Venn diagrams and set notations. Now, this is a relatively new topic to most of the grade 10 and 11 learners. So I'm going to do a 5-part series. This is part 1 of the 5-part series. So I'm going to start off by just talking about the general stuff, the notation that we use whenever we talk about set theory. Okay, so in mathematics, a collection of objects is called a set. So you have got a set of numbers or set of days in a week, and we are going to represent a set by using capital letters. Let me bring in some more things that we talk about. When we talk about the members or the elements of a set, these are what is inside a set. You will see I'll do 2 examples to show that. And then we have 2 ways of describing sets. We can either describe a set by listing or describing whatever is in our sets. And I'm also going to do a few examples later on. So the symbol we use is this funny looking A, but it's a Greek letter epsilon, and it represents where you are talking about an element of or a member of a set. So when we draw a line through it, it means that whatever we are looking at that particular set is not an element of that set. So let's look at the 2 ways that I mentioned. You can either do by listing. For example, you use the commas to separate the elements or the members in the set. This is set A is equal to 1, 3, 5, 7, 9. You can see they have been listed. All right. You can also describe them. You can also say set A is equal to the odd numbers that are between 0 and 10. And here you have got set B equals to A, E, I, O, U. So these are the vowels in the alphabet. Okay. So this is supposed to be small letter. So what we are doing is we can also simply just say the set of vowels. When I bring in another set here, set A equals to 1, 2, 3, 4, 5, 6. We can just say this set is the integers from 1 to 6. Now integers are all your positive whole numbers or negative whole numbers and 0. So we can go into detail later on when we use set builder notation. The brackets, they are the curly brackets you see, they are read as the set of. Okay, so when you do this one, you can say that B equals to the set of the vowels that you find in the alphabet. This is A equals to the set of numbers 1 to 6, or the integers from 1 to 6. In as I was mentioning already, so let's take for example set A, which equals to 1, 3, 5, 7. Then we can say that 1 is an element of A or is a member of that set. 3 is also a member of set A, and 7 and so on. All of these members can be listed or read as an element of the set. Now whatever is not there, like for example the number 2, you then say 2 is not an element or is not a member of set A. Or even 4 will therefore be written as 4 is not an element or not a member of set A. Now the number of elements in a set is very important. You are indicating them by having a small letter n here, and in brackets you are referring to that particular set you're talking about. So the number of elements that you have in set A is 1, 2, 3, 4, 5. So there are 5 members, 5 elements, and that 5 is called the cardinal number. I'll talk later about the number of an empty set when I go further in my second part of this 5-part series. So this is therefore the total number of elements. So whenever you are given something like this, it will be small letter n, and then in brackets, then here will be the set that you are referring to, normally in capital letters, whether set F or A, and then you just have to give the cardinal number, the actual number of elements in that particular set. So let us just look at a practical example. So we have got an example here. We have got the letters of the word food that is in set C. And you're supposed to list the elements or the members of this word. Now you have to be a bit careful, and you will see. So I only listed F, O, and D, but you can see there are two O's there. So when we are listing the elements of a set, identical elements are not repeated. So while they are asking you to now say what are the number of, to write down the number of elements in that particular set, you will go to your listing and you will say that there are 3 members in that set. Okay, the identical one is therefore not repeated. Example 2, list the elements of set F, which is equal to days of a week. Now, the second part is asking, is April an element of F? And then we have to state the number of elements in set F. So this is quite straightforward. You know that there are 7 days in the week, so the number of elements of set F will equal to 7. And April is not a day of, is not a weekday, so it's a month, so it's therefore not an element of the set. Monday, Tuesday, Wednesday, Thursday, Saturday, and Sunday. So a second example, for example, we can have is you are given a set D which contain the letters of the word probability. So we have to list the elements of set D. So remember from a previous example where you have a repetition like the B's, for example, and the I's, we're not going to list them twice. And then we're going to use our listing to find the number of elements in set D. So when I did that one here, the number of elements of set D is equal to 9. And when I've listed them, PROBAILTY, I did not repeat the B as there are 2 B's in the word. I also did not do the same for the I. Another important concept that you need to understand that is often confusing a lot of students is what we refer to as set builder notation. And set builder notation is just a short way of writing these elements that are being described by something that they have in common. So let's look at the set A that I had for my previous example. So I can write this as A is equal to, or set A is equal to X, and here you must be careful, we read this such that, can you see that? X such that X is an integer between 1 and 6, or you can say set A is equal to X such that X is greater or equal to 1 and less than or equal to 6, where X is an integer. So the way that you read it, as long as you understand what is in the set, so you can also, for example, write it from this set builder notation or set builder notation form back into listing them. As long as you have an idea what is it that is in the particular set, that is the most important concept here. So let me bring in 3 other more examples here. So I have here set J which equals to X, such that X is an integer. Now the Z that we have here represent integer, and there is an integer between, and here you must be careful, X is greater or equal to -1, but X is less than 3. So if I was to list them, all right, you can list all the integers. Remember, integer is a number that is a positive or a negative whole number, including 0. So -1 will be part of our solution, but not 3, because it's not all equal to. So therefore, this particular set will only have 1, 2, 3, 4, as you can see the elements that are there, the number of elements there. So the set of, you can read this as the set of all elements X, such that X is an element of integers greater than or equal to -1 and less than 3. And now there's also something important, is when we talk about finite and ending, something that ends, and an infinite set, and something that doesn't end. And this is an example of a finite set, because there's only an exact number of elements of members that your set can have between -1 and 3 not included. Let's bring in another set builder notation, and then we find it in listed form what it will be. So I have got set K which is equal to X, such that X is an element of all natural numbers. Now natural numbers are like counting numbers 1, 2, 3, 4. These are natural numbers to you. But here's the thing, that those numbers we're looking for should be less than 9. And we can actually list them that are less than 9. All counting numbers, all natural numbers less than 9 are from 1 up to 8, but 9 is not included. Suppose this was x is less than or equal to, then we would have listed the 9. So this is also an example of a finite set. The elements don't continue. So if I bring in another one here, L, set L is that, you see here we now use a different letter. So why are all elements such that y is greater than, so it's first of all we know it's an integer, but then it's greater than 3. Now here you must be careful. All integers, remember, whole numbers, positive whole numbers in this case, all integers that are greater than 3, obviously 4, 5, 6, 7, and it goes on and on and on. And this is an example of an infinite set. It will never end. Okay, so this is how sometimes you would see things like when they describe here, they can have y is an element of, and then they have this with a little plus there where they refer to the integers that are positive numbers. So these are also one of those possibilities that you can have. So let us just look at the common set of numbers that you are supposed to be used to, that are using in everyday life. So natural numbers are denoted or represented by that n. Whole numbers, sometimes they put n sub-zero. Integers, always then they have that z there. Sometimes they put plus if they want to talk about the positive integers. Rational numbers, irrational numbers, real numbers are all the numbers that can fit on a number line. Imaginary numbers and complex numbers, we're not going to do those for now, but these are the type of notations. You normally see them in your textbook somewhere in the beginning. So let me just briefly summarize what we have so far. So what we have here is just a quick way to look at a few common numbers that we're using. So the n is represented by either what is natural numbers, numbers like 1, 2, 3, 4, and so on, or counting numbers. Natural numbers, 0 is included. Counting numbers, well, obviously you start counting from 1, isn't it? So what we realize is that the number of elements in the set of natural numbers is going to be endless, it's infinite. And then we tend to use the letter Z to represent integers. And integers are positive or negative whole numbers. Like for example, 1 is a positive number and it's also a negative whole number. So negative 1 and 1, 2 and negative 2, 3 and negative 3, 5 and negative 5, and so on, including 0. These are known as the set of all integers, and they are also going up to infinity. When we just simply say z with a positive there, we are just referring to the positive integers like 1, 2, 3, 4, 5, 6, and so on, also infinite. When we use a Q normally is representing what we refer to as rational numbers. These are numbers that can be written as a fraction. And a number that can be written as a fraction, the denominator of a fraction cannot be 0, because if the denominator of a fraction is equal to 0, that number does not exist. And then we have got real numbers, which we always denote or represent by this capital R here. And these are all the numbers that can be represented on a number line, whether it's the square root of 5, whatever, rational number, irrational number, all the numbers you're working with basically are then real numbers. So let's bring in a few examples to see whether what we have done we actually can take into consideration now. So I have got some few questions here. I want you to list the elements of the members or the members in the following set. So this is set D, and set D is an element of all natural numbers and such that x is less than or equal to 5. So again, if you were to list them, 1, 2, 3, 4, and 5. But remember that 5 is included because of that or equal to. The second one, we have got set E is equal to x, where x is equal to x, which is an element of all integers, and the integers between -4 and 4. You must be careful. -4 is not included, as well as 4 is not included. So when you list them, you're only going to start listing from -3, -2, all the way up to 3. You cannot include 4 because 4 is not included, as well as -4. Then another one is that F says that x is such that x is a square number that is between 20 and 100, or a number that is greater than or equal, greater than 20 and less than 100, but that number should be a square number. So we know our square numbers that are greater than 20 and less than 100. It's 25, 36, 49, 64, and 81. So this is how you list those ones. Then another one is set G, which is x such that x is a positive integer and is a factor of 18. So we can think of numbers that are positive integers, so it means positive whole number, and these numbers are numbers that go into 18 without leaving a remainder. So that will be 1 and 2 and 3 and 6, 9 and 18 itself. Let's look at our second example. So what we have here is we are asking you to write the following set in set builder notation. Right. So you can then say h is equal to x such that x is an even number from 2 to 8. That is even fine. And this one here, careful, because you can see it's an infinite set here. So the moment we're going to start writing it is we're going to indicate by what that is going to be an element of. So we can say that, well, x is an element of all natural numbers and x is an odd number. Okay, it would not have made sense to say integer there because there are the integers that are not included in odd numbers there. And this one here, okay, you can see that if you look at these numbers, these are numbers that can go into 12 and they are positive whole numbers. So you can say x is such that x is a positive integer and is a factor of 12. So when you look at this particular one here at D, so you have got L, the set L is equal to, you have got -2 up to 3. So you can say, well, x is an element of all integers such that x is greater than or equal to -2 or less than or equal to 3. So there are many ways that somebody can write this particular problem here. Well, I'm just going to take this part here because this part can also be written. If somebody wanted to write it, can say, well, x is, let's say, is less than 4. Okay, so less than 4, 4 is not included. And then we can say it's also greater than -3. So that is also one way that someone can write that part there. Another way that someone can write this is we can say x is, well, less than or equal to 3, as you can see. That is fine. And then we can say it is also greater than, as I indicated, equal to -2, which is the one that I have taken. Another one you can say is you can say x is less than or equal to 3. And another side, you can say x is greater than -3. When something is greater than -3, it means -3 is not included. Or another way that someone can do it, you can say x is less than 4. So numbers less than 4 are numbers like 3, 2, and so on. And then x is greater than or equal to -2. So you have got 4 ways of writing this particular story here, but I tend to like this method here because it is considering everything that I am thinking of. So x is greater than or equal to -2 and less than or equal to 3. So had someone write in this form or this form or this form, it will still make sense. So I'm going to upload later on part 2 or 5 of this topic. Thank you.